Ceva's theorem is about triangles. Here is a triangle or a two-dimensional simplex. Let's pick up a point on the side P0, P1 of the triangle and draw the line, call it P01 because it's on P0, P1, and draw a line from P2 to P01. Such a line is called a Cevian, and the point at which the Cevian crosses the side opposite the vertex is called the foot of the Cevian. Here are other two feet in this triangle, P12 and P20. We call such a set of 3 feet a multipede, P01, P12, P20. Let's draw now the Cevians that go to P12 and P20. So here is a Cevian, and here is another Cevian that go to P20. And so it happens that the 3 Cevians concur at one point, this point P. And the theorem, Ceva's theorem, is a necessary and sufficient condition for a multipede of 3 points to consist of the feet of 3 Cevians that concur at one point. So to describe the condition, the necessary and sufficient condition, let's look at the sides of the triangle. If we look, for example, at this side here, P0, P1, we see that P01 divides it into two subintervals, the orange and the green. We call them cells. So here are the cells C0 and D0. And similarly, the interval between P2 and P1 is divided by P12 into two cells, orange and green, call them C1, D1. And finally, the last side is also divided into two cells, C2, D2. And so you see that there is a cycle of pairs, orange, green, orange, green, orange, green. And the condition says that when you go along this cycle and you take the ratio of the length of the orange to the length of the green and you multiply them, you get 1. So C0, the length C0 divided by the length of D0 times C1 divided by D1, C2 divided by D2 is 1. And now we want to generalize Ceva's theorem to simplex sets of higher dimension. So a triangle is a simplex of dimension 2. We want to do it for general simplexes of dimension n, and we are going to depict it, to describe it only for a tetrahedron because it's easy to draw it. So next we go to a tetrahedron. So here is a tetrahedron with 4 vertices. It's a simplex of dimension 3. And let's start with picking up a point P inside the tetrahedron and take the Cevian that goes from P3 through P, and it hits the face opposite P3 at point P012, which is the point on the simplex P0, P1, P2. We can take another Cevian. Here is the Cevian that goes from P0, and its foot is P1, 2, 3. And then we can take also Cevians from P1 and P2 through P. So these are four concurrent Cevians that generate 4 feet. So a multipede in this case will be these 4 feet of the concurrent of the Cevians on each one of the faces, on the two-dimensional faces of the tetrahedron. Only that now we can do something else. We can use the point P012 to create new Cevians now on the face of the simplex. So starting at P0, we have a Cevian that ends at P12. Starting from P2, we have a Cevian that ends at P01, and then again a Cevian that from P1 that ends at P20. And we can create also points on the other edges of the feet, on the other edges of the tetrahedron. And altogether, we are going to have 10 feet, really, 4 on the two-dimensional faces and 6 on the one-dimensional faces of the tetrahedron. And now the question we are going to ask is exactly the question we ask about the triangle. Given a multi-P that consists of 10 points, one for each non-trivial face of the tetrahedron, we want to find a necessary and sufficient condition such that these points are generated by concurrent Chevians, now concurrent not only in the whole simplex but also in all its sub-simplexes. So first of all, let's look at the fit that lie on one-dimensional faces of the tetrahedron. There are 6 of them. And we'll see that a necessary condition for this fit to come from one point P from concurrent Chevians all over, the condition is very similar, the necessary condition is very similar to the one we know from the triangle. Let's start with this side here, one-dimensional side where P01 is. P01 divides this side into 2 cells, orange and green, call them C0 and D0. Then let's go to this side, P1, P2. It is divided again to orange and green. Then the side P2, P3 is divided to, so the previous one are C1 and D1. Now we have C2, D2, and finally we have on the last one C3, D3. So now we have 4 pairs of cells. You see that the cells are again arranged in, we don't go through all cells, we go only because we need only a cycle. So this is a cycle of pairs of orange and green. And the condition, the necessary condition is exactly the same as in the case of triangle. The ratios of length of Ci to Di along the cycle, the product of these ratios should be 1. So the generalization here of the necessary condition is that we simply need to take cycles of pairs of orange and green and take the product of the ratios along these cycles. There are several cycles of length 4. There are also cycles of length 3. And in all of them, it's necessary that in all of these cycles, the similar equation holds. Now we want to look at the fit on the 2-dimensional faces, the 4 fit on the 2-dimensional faces of the tetrahedron. To do this, we spread the faces of the tetrahedron in the plane so that we can look at it more easily. So here is one face, P0, P1, P2. Next to it, the face P1, P2, P3. And here is another face. And this is the last face, and you can see that this side of the face is exactly this side. So we can wrap it. So there is a cycle of cells, a cycle of faces here. And in each one of these faces, we have a foot. So here is the foot P10, P012 in the first, P123, P130, P320. So we have 4 feet in each one on each 2-dimensional face. Now, the point here, this point here, doesn't divide the face into 2 segments as before. Before we had cells that were 1-dimensional. Here we can have 3, but we need only a pair of them, any pair. Let's take this pair. So here is a pair of cells, the orange and the green, call them C0 and D0, which are created by the foot P012 in the face P0, P1, P2. And here are 2 cells, now 2-dimensional cells in the 2-dimensional face of the tetrahedron, and they are generated by P123. Here is, so you call them C1 and D1, and here there is another one. This will be C2, D2, and this will be C3, D3. And you note that D3 is really adjacent to C0 because P0, P2 and P0, P2 here are the same side. So we have a cycle of pairs of cells, CIDI, and a necessary condition for the P1, 2 of these fit on the two-dimensional faces, a necessary condition that these fit come from a single P here, that is from concurrent Chevians, is exactly the same condition. But only now that what we have to understand that this term here, C0 with 2 bars, is not the length of C0, but rather the area. So the ratio of the areas of the orange to the green along the cycle, the product of these ratios should be 1. So we found necessary condition. When we add all conditions, and when we add all these conditions together, when we require that first of all, we have to define properly what exactly we mean by cycles of cells. But when we define it precisely, then the requirement that along any cycle of cells, one-dimensional or two-dimensional or mixed ones, even if on all these cells we have this condition that the product of ratios is 1, then this is a sufficient condition also for the multipede to come from a single point P and the concurrent Chevians it defines.